Okay, so let's continue number 6. So remember from the last video, this was our recurrence relation. Okay, so now we wanna explore this recurrence relation and hopefully be able to compute, right, or determine our C1, C2, and so forth, right? We want to find our coefficients. Okay, so let's go ahead and start. Also, to find the pattern, I'm going to start with if n equals 0, well, what do we get? Well, if n is 0, then this is just 0 plus 1, so I get C1, and that's just half of C0. Okay, so there's kind of one relationship. What if n is 1? Well, if n is 1, again, 1 plus 1, obviously 2, and then it's half of, well, if n is 1, that's just C1. But remember, we know what C1 is, right? C1 is right there, so I can, simplify this a little bit more. I get half of C1, which is just half of a half, and half of a half we know is a fourth. Okay, so there is another relationship. All right, notice it's in terms of C naught in C naught. And whoops, let me get my white here. So if n is 2, well, if n is 2, then we have C2 plus 1, or C3, and that's just going to be half of C2. And again, we found C2. It's just above, right? C2 is 1/4 C naught. So then C3 is 1/8 of C naught. So another relationship. And how about n equals 3? Well, if n is equal to 3, again, 3 plus 1, so we're finding C4. So C4 is, and then it's just half of, and n is 3, so half of C3. But again, we know what C3 is, right? We found C3. So half of 1/8 C naught, and that's just 1/16, right? Hopefully you start seeing a pattern here. We're getting nice powers of 2. And again, we can continue in this manner. And you can, I would go up to, you see the pattern. So we can kind of generalize what this is going to look like. So maybe we can say our Cn, right? It's probably going to be, let's see, Cn is going to be, well, maybe if you want. Let's actually, because this is going to help in other examples as well. So if I write, okay, so C2 is, it was really a half times a half, so, or you can say 1/2 squared, C naught. C3, if you'd like to say 1 over, right, that's really 2 cubed of C naught. And then notice C4, right, that's really, so maybe equals, right, 1 over, well, that's just 2 to the 4th C naught. So notice it's just C naught divided by the power, right, 2 to some power of n. And our n, we started with n equals 1. So we can probably conclude, right, our inductive reasoning here. We can say our Cn is probably going to be, well, we can say half, 1/2, I don't like how I wrote this. It's going to be 1 over 2 to the n, that's an n, times C naught, right? Or if you want to say C naught over 2 to the n. Okay, so I'm going to call that my Cn, right? They all look like that. If you just, again, plug in our n equals 1, you're going to get our values above. So remember our power series solution, right? We assume that it was a power series solution, it looked like, right, this, we assumed this earlier in the problem in the last video, n equals 0 to infinity. Okay, so let's expand this. Again, what does this mean? Okay, this means if we plug in C naught, we get C naught x to the 0, which is just 1, plus C1 x to the 1, plus C2 x to the 2, or x squared, plus C3 x to the third, plus dot dot dot, right? We have our infinite sum, and we found our CNs. So let's, we can input these CNs. And actually, I forgot to write one thing down, right? This guy is, right, we still have our x to the n. That's an n. And let's see, notice that we can, okay, so let's substitute our C0 plus, so I'm going to substitute, so we know what C1 is, C2, C3, right? We found all these guys up here, right? There's my C4, C3, C2, right? C1. Okay, so I'm going to input those values since that's what they are. So C1 was half, whoops, well, I could write it in green, but half of C0, right? X plus what was C2? Well, that was 1/4, right? Or 1 over 2 squared, C naught, x squared, plus C3, which was from above, 1/8 C naught, or 1 over 2 cubed, x to the third, plus dot dot dot, 3 dots, x to the n. Okay, so again, here's my C1, C2, C3, and so forth. And then just using some algebra, we can factor out a C naught, which we want to, and we're left with the following. Let's see, we have 1/2, actually we have an x there. Let me make this a little bit neater. Okay, so we have 1/2 x, right? Again, I'm just factoring a GCF plus, let's see, we have 1 over 4 x squared plus 1 over 8 x cubed, and let me do this, x to the n, and I can erase these brackets. Okay, so again, nothing really hard. I just, again, input my CNs, and I factor out my C naught. And again, this is up to you if you see the pattern quickly or not. I want to rewrite this as 1 plus, okay, this is really x over 2 plus, and then again, from above, I know that this is, okay, so I'm going to write this as 1 over, well, maybe I'm going to write this as x over 2 squared, right? That's just x squared over 4, hopefully you see that. And then this is really x over 2 cubed, right? That's really x cubed over 2 cubed, which is 1/8 x cubed. And let's see, let's write we still need our x to the n, and here I really should have plus dot 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 because it's an infinite sum. So notice we wrote this power series, right, in terms of what? In terms of this x over 2, x over 2, x over 2. And again, the problem says we want to rewrite this in terms of elementary functions, so the functions that we're familiar with. So maybe note or recall, right, from page, I think it was 195, that 1 over 1 minus x, that's our geometric series. And that is the same thing as this guy. And again, this is just in your book. 1 plus x plus x squared plus x cubed plus dot dot dot. So this looks very similar. Not exactly, right? Instead of what? X, 1 plus x squared plus x cubed, we have 1 plus x over 2 plus x over 2 squared plus x over 2 cubed. So we can, there's a relationship here. There's, we're going to, instead of x, we're going to use these guys, right, instead of our just x. So we can rewrite this in the following form. So we have, again, y of x equals, right, this was our y of x. Well, we can write this as c naught times all of this. But all of this is really 1 over 1 minus, so it's not 1 over 1 minus x, right? But because, I mean, it could be x, but in this case, we have x over 2. Okay, so we wrote this in terms of our geometric series, 1 over 1 minus x. Just doing some algebra, right? You can multiply everything by 2. So we get, let's see, and easier here. We can just say 2c naught over 2 minus x. So this is your solution, and it's definitely a power series, right? Again, in terms of this guy right here. Okay, so the second part, see, I'm at 11 minutes. All these problems they're tedious. They're not bad. They're just very tedious. Let's see. Let me see if I can do the last part. So the next part is finding the radius of convergence. So find the radius of convergence. Okay, so radius of conversion is going to be, from your book, rho is equal to, again, assuming the limit exists, the limit as x approaches infinity of the absolute value of our cn's over cn plus 1. Now here, right, our cn's, right, our cn's are our c naught over 2 to the n, right? That's what we figured out from above. Okay, so we're just gonna use a formula. So the limit as n approaches infinity of cn, okay, that's just c naught over 2 to the n divided by, right, that's my divided by, c to the n plus 1, which is just c naught over 2 to the n plus 1. And this is, again, the limit as n approaches infinity. This is just really c naught over 2 to the n. I'm dividing fractions. So multiplying by the reciprocal, that's gone. So the limit as n approaches infinity of 2 to the n plus 1 over 2 to the n. And the limit as n approaches infinity, and this is just 2 to the n plus 1 minus n using our fun law of exponents from algebra. And we are just left with 2 to, well, n minus n is 0, so we're left with 2 to the 1, or 2. Well, the absolute value of 2 is 2, so then the limit of a constant is just the constant. So that is our radius of convergence. Rho is equal to 2. And let me quickly see what the last part was. It says, let's see, and use the series, identify the series, and oh, we already did it, in terms of familiar functions. So that's it. That's number 6.